Private addressing and NAT. The biggest problem the internet has ever faced was as a direct result of its own exponential growth. Simply put, we are running out of IP addresses. Private addressing and NAT are two short-term methods proposed to help solve this problem. In this nugget, we're going to take a brief history lesson to set up the problem of IP depletion. Then we'll look at private addressing and see what it is and how it can help, followed by a discussion on network address translation as it was initially proposed. And we'll end up with a look at port address translation and a discussion on how it was an improvement over classical NAT. In the early days of the internet, IP addresses were handed out in groups called IP classes. These classes had a big problem though. They were very wasteful. To give you an example, if a Class A address was assigned to a large company, it had the potential of 16 million hosts. Even with subnetting, you'd be hard-pressed to use that much address space. Couple that with the growth of the internet, and you can see why we were running out of IP addresses. As the internet community frantically looked for a solution, something came to light, that the host in an average enterprise network could be divided into three categories. Here we have them here. The first category needed no communications outside of an enterprise. Everything they needed was inside their local network or their local subnets within the company. The second group, they needed no communication outside of the enterprise except for a few special services. So it wasn't that often that they went out to the internet to connect to a device. And then the third group, the majority of their communications were outside of the enterprise network. This diagram illustrates the three groups. The first group is subnet A. All of its communication happens between subnet A and B or A and C. The second group, subnet B. Most of its communications are between A and C, but a small percentage will have to go out into the internet and access some service. In the case of this example, it's HTTP, which is a web service that it needs for maybe partner information. And the third group is shown here in subnet C. Most of its traffic has to go out to a partner network and communicate with another subnet, and it's out on the internet, and it has a very small percentage that it has to do internally. This was really good information, but what could be done with it? You've got to realize that back in this day, any computer that was connected to the internet, as the computers in these subnets would be, had to go through a registration authority, IANA, which is the Internet Assigned Numbers Authority, and get an IP address space so that they could apply one of those IP addresses to each computer. This was bad enough in the cases where we had a subnet like A that only communicated within its enterprise and never had to go out to the internet. But it was even worse because some companies were setting up intranets with the purpose of never connecting to the internet. Still, those intranets had to have globally unique IP addresses that they registered with IANA and assigned within this network. Now, companies that are connected to the internet could not get that same IP address because it belongs to somebody. A short-term solution was proposed in RFC 1597. Essentially, it was the registration authority, which was IANA, the Internet Assigned Numbers Authority, coming forward and saying, we do have addresses that we assign specifically to companies that nobody else can use, but we're also going to come up with a set of addresses that we're going to call private, and therefore every entity to use as long as these hosts are not connected directly to the internet. Key in on the fact that I call this a short-term solution. IANA was aware this wouldn't alleviate the problems in the long run. In fact, the internet community saw the long-term solution as IPNG, stood for IP Next Generation. This idea would later evolve into IPv6 as we know it today, but not in this time period. But as far as private addressing and alleviating the problems of the day, it was a good short-term solution. These private addresses could be used in large enterprise-type networks like we saw earlier. Here we have a subnet that will only communicate with the subnets within the enterprise and never go out to the internet. We'd apply a private address there, 192.168.1.0 with a 24-bit mask. The second class of hosts that we had were hosts that would communicate within the enterprise and then have a small subset of traffic that had to go out to the internet. In this case, for our example, HTTP traffic to a web server. So what the proposal in 1597 as an RFC was set up an application gateway. Give it the private address space so it still can't go out to the internet. Have it go to a machine internally, and that machine will proxy its request out to the internet and back. It had other advantages as well. For those of you that have used proxy servers, you'll have caching here. This whole subnet is addressed publicly 192.76.28.0 with a 24-bit mask. I pulled this address out of the RFC as a public address, and it could be used to route out to the internet anytime it needed to be. Private addresses were also used in the intranet space to free up public addresses so they could be assigned to companies that did connect to the internet. So we'd see an intranet here with a router and two networks or maybe more on each side with a private address space. In this case, 10.1.0.0 with a 16-bit mask, 10.2.0.0 with a 16-bit mask. Even though private addressing was able to alleviate a lot of these problems, it wasn't without controversy. In fact, another RFC came out 2 or 3 months later, RFC 1627, that said, in its whole, this is a very bad idea, and IANA overstepped its boundaries as a registration authority. The problem was network readdressing. If you had a network one day, they could use private addressing because it didn't go out to the internet, and then sometime in the future, it was destined to go out to the internet, you'd have to change the IP addresses and all of the computers in this subnet. 1597, the original RFC, said, hey, this isn't a big deal. RFC 1627 says, yes, it is, especially in the case of an intranet, because these things can go rather large, and you could have many subnets here, and you have to readdress every PC that's on these subnets. Another reason private addressing was coming under fire was that the popular short-term solution of the day was CIDR, which stood for Classless Interdomain Routing. Essentially, it was doing away with the original proposed classes. If you recall, we talked about a Class A address being assigned to a company, and it had the possibility of over 16 million hosts. It was pretty wasteful. So this was just a smarter way for the registry authorities to hand out IP addresses to companies. To use a metaphor at this point, private addressing was a damsel in distress and really needed a hero to come save the day. That hero was known as NAT, short for Network Address Translation, and it was proposed in RFC 1631. The authors of this RFC were very aware of political positioning and appeased everybody. They started off by saying, we understand the long-term solution is IPNG, next generation. We also understand the popular short-term solution is CIDR. We think CIDR is a good idea too, but we also know it's not complete yet. What if it's not complete in time to bridge the gap between the short term and the long term? Another point, what if once it is completed, it's not adequate? In other words, it needs some help. With these two facts in mind, let's keep private addressing and let's add a little twist to it called NAT. NAT at its core is simply mapping a private address to a public address for transmission over the internet. Remember that the big problem NAT is addressing is that once you had a subnet that was privately addressed because it was never intended to go to the internet, then somebody changed their mind, as always happens with network protocols, and it had to be connected to the internet. Instead of readdressing every one of these PCs, let's simply put in a couple of commands into the router, get a public IP address space as you would have anyway, and map the two together. This proposal also brought forth a couple of new terms. First of all, the private address space was termed the local IP group. The public address space was the global IP group, and there was a mapping pool that consisted of IP addresses. In the case of our example, 192.76.28.3 to 254 were available in this pool for mapping. So in the case of our original network diagram, where we had a subnet here that was privately addressed because it only communicated within the enterprise, and then later we had a need for public addresses to communicate with the internet, instead of changing each one of these PCs' IP addresses, we're going to simply map this private address space to this public address space here and move our traffic across. Keep in mind that there is nothing that you have to do on this distant end subnet to communicate with this subnet here. It's completely transparent that we're doing any NATing. So a packet that comes from a PC here will simply be destined for 192.76.28. Whatever address was pulled out of the pool. When it gets to this router, the conversion will take place and it will go to the privately addressed machine. All right, when we're talking about intranets, the same benefits occur. We originally had privately addressed subnets here that were just going to talk to themselves. At some point, funding came through or expertise within the company, and you connected to the internet. Instead of readdressing every one of these subnets, simply put in a few NAT commands, get the public addresses that you were going to get from the registry, and map the two. Looking at communication through a NAT device in more detail, we're going to find that there's 3 distinct addressing steps. Here's 1, 2, and 3. Let me set up our diagram. I have a computer N1 connected to a router, and it's the local router, connected to the backbone, which in this case is the internet, connected to a distant end router, and then to a computer named N2. What I want to do is I want to telnet from N1 to N2. Now, these devices here and here are going to be performing NAT functions. So let's see what we wind up with. At N1, I have a packet leaving with a source IP address of 192.168.1.3. As you can see, that's its own IP address, and a port number of 1025. Remember that port numbers are in reference to TCP or UDP protocols at the transport layer. Now the destination address information, destination IP is going to be 192.76.29.3. Kind of interesting though, because we said we're going to telnet from N1 to N2. N2 has an IP address of 192.168.4.3. Not what we're seeing here, right? The reason for that is this. IANA, when they came up with private address spaces, they said these addresses will be reserved for private use, and the other part of this, the rule will be that the routers on the internet backbone cannot route packets destined for those subnets. So we couldn't get a packet from here to here if the destination address was this private address space. So we give it a public address, and the NATing function in this router is going to map this public to this private. Okay? Next, the port 23. That's the well-known port number for Telnet. And as we said, we're telnetting from N1 to N2, so that makes sense. All right, number 2 here, this is where the addressing is going to change a little bit. It gets to our router, and this is the first NAT step. What it's going to do is take that source IP address and change it from the private to the public, 192.76.28.3. It'll save in its memory a mapping that says these 2 addresses are for the same computer. The port's going to stay the same, 1025. No need to change it. The destination information stays the same as well. All right, that packet traverses the internet and finally gets to the distant end router. Once it's there, another change has to take place. The source IP address is going to stay the same as it was in the router when it left here. 192.76.28.3, port 1025. Now we'll see a change here. The destination IP address is going to change to 192.168.4.3. Why is that? Just like we discussed earlier. To get to this point, we had to use a public address. To get beyond this point, we have to use the private address, the address that is really assigned to N2. So that's the destination IP. The port number stays the same, and our packet arrives at N2. In this communication path, we saw 2 IP address changes, one here and one here. But you might be asking, why did I change the source IP address if I want to get a packet from N1 to N2? Because the rule was that you couldn't route to this private address space. But it didn't say anything about routing from a private address space. And that's true. If we wouldn't have changed the IP address here from the private space it was, that packet would still arrive at N2. No problem at all. The problem would have been this. When N2 tried to send a packet back to N1, because Telnet and most all other protocols that we have in the internet talk both ways, it wouldn't have made it because it would have tried to send it to what it saw originally as a source address. But because we changed it here, when N2 replies, it's going to send its reply back to 192.76.28.3. It will get that packet this far, then be converted back to the private space to get to N1. NAT served as a great hero for private addressing, but then it ran into a few problems of its own. Note in my subnet here I have 254 PCs available, and if I add another private address subnet here, I have another 254. I have well over 500 PCs that are privately addressed and would like to get to the internet. Within my pool, I only have 252 possible IP addresses. At some point, all the mappings will run out, and anybody else that tries to get to the internet after that point will be denied. As with any good hero in any good story, NAT saved itself by transforming into something a little bit different. In RFC 3022, NAT now, as a definition, had classical NAT, and it had something new. It's called Network Address Port Translation. The shorter nickname for that is PAT, for Port Address Translation. Let's look at how they work. First of all, classical NAT. We just went over this in our last example. On the private side, I have a source IP and a source port in my packet. I have a destination IP and a destination port in my packet. When I get to the NAT device, this is the router, I have a pool of addresses to choose from between 3 and 254 in that 4th octet. So I change that IP address in the source to a new IP, keep the same port number, the destination IP and port stay the same as well, and I'm off to the distant end, right? All right, it's a little bit different in PAT. Because remember, in NAT, I have a pool of IP addresses. PAT is the answer to that pool being depleted, and I'm down to 1. So let's say all I have is .3 available. The first packet that comes through here has a source IP, a source port, a destination IP, a destination port. Runs through my PAT device. Now it's going to get a new IP, and that's that .3 in the 4th octet. This is what's going to be a little bit different, though. It's going to get a new port number. This port number has to be above the well-known port number, so anything above 1024. So let's say it's 1025. The destination IP and port stay exactly the same, and it's on its way. All right, after I've sent that out, another entity comes in, another PC, and wants to send a packet. It has a source IP, a source port, a destination IP, and a destination port. When it gets to the PAT, the only IP address available is .3, right? So it gets a new IP in reference to what it used to have, but it's the same IP in both of these instances. And it gets a new port. This is where it's different. Here, remember I said let's give it 1025. Here I could supply 1026. Destination IP and port stay the same, and this packet's on its way. So you got to ask, if I'm dealing with the same IP addresses, what happens when this packet finally returns, and then this packet finally returns? How does this device know who to send it to? The answer comes in this port. This is what it's used as a tracking device. When this IP packet comes back destined for port 1025, he knows that belongs to PC number 1. When this packet comes in destined to port 1026, this device knows that packet is destined to PC number 2. Let's take a detailed look at 2 different devices that are privately addressed, as we see here, N3 and N1, trying to communicate over a PAT device to the same distant end. First thing we're going to get is N1 sending out a packet with a source IP of 192.168.1.3 and a port of 1025, a destination IP of the distant end, and a port of 23 because it's a telnet packet. All right, in step number 2 right here, now we're at the PAT device, we're going to get a new IP address. The new IP address in the source is 192.76.28.3. It's the only one available. We're going to get a new port address as well, 1026. The destination information stays the same, and we send this packet on its way until it gets to the distant end router. At that point, we keep the source information the same, we change the destination address to make this last leg as we did in our other examples, and we've communicated to N2. All right, so that's from N1. Now let's look at a packet from N3. The source is going to be IP address 192.168.2.4, as we see here, and the source port is 1025. It's the same port that they use up here because they're different IP addresses. You can do that. Destination, IP, and port just as it was above. Now we're going to get to the PAT device. We get the IP address of 192.76.28.3 again because it's the only one available. So these 2 addresses are the same. So you got to have a point of distinction, and that's found in our port. Our port is going to be 1027, so it's going to increment up from the last one that was assigned. Destination information stays the same. The packet rides over the internet to the distant end router. Source information stays the same. The destination IP changes to the private address, and the packet is delivered to N2. All right, so as we said in our last discussion, what happens when this packet comes back? The first one we sent there, and the second one here. They're going to have a destination IP address of 192.76.28.3. In both packets, they're the same. Here's the port. The port for 1026 will come in this packet, and the PAT device, which is the router, keeps a map that says, I know that port 1026 goes to N1. In the second packet, port 1027, there's a map in the PAT device that says, I know that port 1027 goes to N3. So all packets are delivered where they should be. So as you can see, the ideas behind NAT and PAT, one giving you a new IP address, another one giving you a unique port number, are pretty simple ideas, but they can be used in very complex scenarios. Let's take a look at our original diagram and see how we can deploy our newfound knowledge. We start with the idea of the original NAT IP pool from 3 to 253, and all these hosts here that are privately addressed can be mapped individually to those IP addresses and go across the internet. But we add the idea of NAP-T, which we refer to as PAT, Port Address Translation. So when we deplete the whole pool and we have one address left, every device that's left can go over the internet with this IP address simply by changing the port number. Take a close look at our diagram and see what that is allowed for. We changed this subnet that used to be publicly addressed with this address space into a private address space, redeployed those public spaces as part of the pool, and then eventually the PAT number as well, so that we can service all of these subnets with one address space. And we did the same on this other end. We moved the private address here, and we moved the public address that used to be there out on the other side of the router to service global addresses to traverse the internet. So now our story comes to present day. Our short-term solutions have become so robust that they might even be long-term solutions. You don't hear a lot of talk about the need for IP version 6. We have to have it today. We have to have it yesterday because we're running out of IP addresses. With CIDR, private addressing, and NAT coupled, we're doing pretty well. Don't get me wrong. I'm not saying that IP version 6 won't be deployed throughout the internet. In fact, I'm sure it will. I'm just excited about the fact that our short-term solutions have worked so well that they're going to get us to the point that IP version 6, when it is rolled out, it doesn't have to be the bleeding edge. It can be the leading edge with all the kinks worked out. So if I'm going to spend an entire video telling you that NAT is an easier way than resubnetting every computer in your subnet, and that the commands are very few, then I better show you the commands, right? All right, let's move into that. First thing we have to do is set up our boundaries, and that is to say we have to have an inside and an outside reference point for NAT to work. These reference points will be interfaces on your router. In the case of our example, we're going to have R1, which is a router, and the inside reference point is going to be Ethernet 1.0. The outside reference point will be Fast Ethernet 2.0. Keep in mind the networks involved as well. The inside network, 192.168.1.0 with a 24-bit mask. The outside network, which is going to be the public addressing space, 192.76.28.0 with a 24-bit mask as well. All right, let's get into the commands. As you recall, to configure an interface, first we have to enter config T, which is configure from terminal within our router. Once we're in there, though, we're going to input an interface, a type, and a number. So in this case, the type is going to be Ethernet. The first number is going to be 1/0. Once we're into this configuration of the interface, we're going to type in IPNAT inside. Again, we're setting up our reference points. Then we're going to do the same thing for the outside interface. Interface, Fast Ethernet 2.0, IPNAT outside. So it'll look like this diagram. Keep in mind that the reason this short-term solution has been around so long is because it's a very simple idea that can be applied in very complex ways. Given that, I'm going to show two examples. One's going to be a static one-to-one NAT. Another is going to be a dynamic pool. Now, whichever example we use, we always have to have reference points, the inside and the outside. So this will always be common, no matter whether we're using static or dynamic type of NAT. Our static command is going to set up a one-to-one mapping from a private address, let's say .3 on this subnet, to a public address .3 on this subnet. So now anytime a packet comes from 192.168.1.3 through this router for transmission over the internet, it will always leave as 192.76.28.3 if this command is in place. The structure of the command is IPNAT inside, because you're saying this is going to identify traffic from the inside interface. Source. This is where you have the option of either source or destination address to be modified. In this case, it's going to be the source address. Static. We don't want this to change. We want it to always be. Then we supply the local IP, which will be here, and the global IP, which will be out here. So let's jump onto the router and apply these commands. All right, the first thing we're going to do is log on, get to the correct user level that we need, and then go into conft, which is configure from terminal. All right, as we stated above, the first thing we got to do is get into a specific interface and then set the reference point either inside or outside. So let me do that now. We're going to use exactly the interfaces that we have in the example. Interface E10 will be our IPNAT inside reference point. Interface Fast Ethernet 2.0 will be our outside reference point. I'm going to cheat a little bit with the up arrows there.
All right, now we're at the static command. Static IPNet inside source static local IP and global IP is what we're going to type in here. So let's do it. IPNet inside. The inside is saying that we're going to use the inside interface, change the source address, make it a static entry. And now the IP addresses that I'm going to use are going to be exactly from the example as well. 192.168.1.3 on the inside, 192.76.28.3 on the outside. All right, and there we have it. Let's get out of our configuration mode, copy from the running config to the startup config. Sorry. And then we'll be able to do a show configuration and see the work that we just typed in. And get to the right place, get through all the serial commands. Here we have the first portion. Interface Ether10 is our IP NAT inside reference point. Interface Fast Ethernet 20 is our IP NAT outside reference point. Here we see IP NAT inside source static 192.168.1.3, 192.76.28.3. Another cool thing to note is when you put in a static command, you can also do show IP NAT translations. And what do you see? You see the inside global is 192.76.28.3. You see the inside local is 192.168.1.3. Don't get confused. When it says inside global, it's just keeping a track of saying that we're going to make the conversion from the inside interface. Here's the global IP address, so this is public to the internet. Again, transition made in the inside interface, this is local, so this is our private address space. Now once we set up a dynamic pool, and different PCs start to use that pool, you'll see this thing get very, very long, and it's going to have a lot of dynamic translations in it. The IPNAT inside source root portion of this command is going to stay the same when we're establishing our dynamic pool. And we're going to see it here, IPNAT inside source. This is where it starts to be a little bit different, and this is why. We have a list command here, and it's going to point to a specific ACL number. So we need an access list. Why do we need that? Remember we had a conversation saying that our pools were usually small, finite IP addresses that we could hand out. And a lot of times the back-end network had far more privately addressed PCs that might want to use this pool. And if we don't limit who can use the pool, at some point we're going to deplete these addresses. So this list is going to say only these PCs from the inside network can have access to this pool under this name. And this name is going to be Nugget for the sake of our examples. So if we are going to point to an access list, we probably better create one. Here's a command to do that. Access-list, the ACL number, permit or deny here, a source, this is an IP address from the inside network, and a wildcard mask to identify it either as a host or a portion of a network. Now that we've defined who can play at the pool, you know, it kind of sounds like the Hilton, a hotel of some sort. It says, if you have your guest pass, now you can play in our pool. But anyway, now we have to set up the pool. And here we do that. IPNAT pool, you give it a name, which is going to be Nugget for our example. You have a start IP, an end IP, and a network mask associated with them. For our pool, we're going to use 192.76.28.4. And we're going to start with .4 because above, right here, we use .3 to be our static address to .3 on the outside. So we're going to start with .4. The end of it is going to be 192.76.28.254. So our pool is from 4 to 254. Let's make this happen on the router. First thing we're going to start off with is creating our access list. So we got to get into the configuration mode again. Access -list. I'm going to number it number 1. We're going to start off with a deny statement. The reason for the deny statement is we don't want to use this portion of our IP address space because it's defined for static. It's .3. So we're going to deny 192.168.1.3. And actually, save ourselves a little time, instead of typing out the whole mask, we're going to type in host here. And it knows that's a specific host. All right, let's add a second line to our access list. Or in this case, all we would do is deny and then be gone. Still, access list 1, we're going to permit 192.168.1.0. And the reason for this is we're going to use this mask that we talked of earlier in setting up our ACLs to set up a whole network for permission. So it's going to be 0.0.0. 255. So let's see how this is read. First of all, it's going to say, if you come in and you're .3, I'm going to deny you. The reason for that is, I want you to read this static statement instead. Anybody else that comes in from that inside network, you're permitted, and now you're going to be applied to this pool. All right, the next thing we're going to set up is the pool. So let's look at our IPNet pool command. IPNet pool, the name is going to be, as I said before, Nugget. I'm going to cap it so that whenever you see the name, you'll recognize it pretty readily with its caps. Have a start IP, 192.76.28.4. Remember, this is the global IP addresses on the outside that we're going to use to hand out. That's why you don't see it as part of the 192.168.1 space that's inside. It has to be the outside. So .4, the end address, 192.76.28.254. And then we define the mask associated with both entries, which is going to be 255.255.0. All right, so far we have our access list. We've set up our pool. Now we're going to set up the key to the whole thing working. We're going to tie our access list to the pool. The command is IP NAT inside source, just as it was in the static command. This time we're going to use a list, though. Type in 1 for the list number. We find that in our ACL here, ACL number 1, and in our pool. So pool, the name, Nugget. Now, this name that you're using is case sensitive. So if I was to type in a lowercase Nugget here, it would come back and say, there is no pool named Nugget. All right, and then there you have it. Now everything is tied together. Let's close off our configuration window. Copy the run to the start configuration. And then once this comes up, we can use the show conf to see the work that we've done. Let me get out of these serial interfaces so that we can see exactly what we're looking for. Remember that we're going to see here the reference point is still in place. IPNAT inside, Ether10. IPNAT outside, fast Ether20. What we're looking for now, though, is what ties our NAT pool to our static entry and brings it all to life. IPNAT inside source, the list is 1 for the access list, the pool is Nugget. And if you go further into the configuration, you'll see your access list towards the end of the show configuration command. Here it is, access list 1, deny this specific entry because it's part of our static pool, our static entry, and then permit everybody else within the inside network. So as you can see, these commands are much easier to put in than it would be to go to every PC on your subnet and change the IP address. But the real value doesn't only come in when you're setting up a network, but as a network runs through its life cycle, there will be many moves, adds, and changes. And as those occur, you can simply come in here and add static entries if needed, or you can enlarge or decrease the size of your pool. In this nugget, we covered a bit of history to show that the internet was running out of IP addresses. Then we saw how IANA's proposal for private addressing could help by offering an ambiguous address space for use outside the internet. Then as private addressing had its problems, network address translation came in and allowed the mapping of private addresses to public addresses so that we could transmit packets over the internet from a privately addressed subnet without having to change its IP addresses. And finally, as NAT pools were depleted, port address translation was introduced, and it allowed multiple privately addressed computers to be mapped to one public IP address by changing its port values. I hope this has been informative for you, and I'd like to thank you for viewing.